Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this set of videos we're going to talk about the theory of the firm, which includes the production process and cost. In this video we're going to introduce the concept of production functions and start learning about a few well-known production functions. Where we're going with all this is that decision making in business is about considering cost and benefit. In these next few videos we're going to be focusing on the cost side of things. Since cost is involved in the production of goods and services, we also need to learn about the production process. We're going to start out by defining the production function. The production function tells us the maximum amount of output that can be produced with a given set of inputs. We're going to write the production function as Q equals F of K and L. Q is the output. That's the amount of goods that our firm is producing. K is capital. In econ, capital has a very specific meaning. It means physical equipment that's used to produce things. We always use a K for capital, I think because C is going to be reserved for cost, which we're going to talk about later on. Finally, L is labor. Both capital and labor are used in the production of output, so we call those our inputs. It's possible to have a much more complex production function with more than two inputs, but we're going to stick with two just to make sure that we can actually do the math. The lessons that we learn from production functions with just two inputs can be applied to more complex functions as well. We will also distinguish between the long run and the short run. There is no specific length of time that determines the short run versus the long run. The difference is, in the short run, some inputs are fixed, and in the long run, no inputs are fixed. The amount of time it takes to get to the long run is simply defined by the amount of time it takes for all those fixed inputs to become variable. This is going to be different for every firm and every industry. For our purposes, in the short run, our fixed input is capital. We will use K star to mean the fixed amount of capital in the short run. This cannot be changed until we get to the long run. What this means for the production function is that in the short run, we have Q equals F of just L because we have no choice over capital. This is going to be equal to F of K star and L. Keep this in mind for now, we'll return to this later. Before moving on, we're going to get a few definitions down. First of all, the total product is the maximum amount of output that can be produced with a given amount of inputs. This is simply defined by our production function. Plug in the inputs, and whatever you get out of the production function is the total product. That's going to be our Q. The average product is the total product divided by the quantity of an input. Remember that we have two inputs, so there's going to be two different average products. First of all, the average product of labor is going to be Q divided by L, and the average product of capital will be Q divided by K. The marginal product is the change in the total product due to an increase in an output. Again, we have two outputs, so we're going to have two different marginal products. Remember that when you hear the word marginal, you want to be thinking about derivatives. The marginal product is the partial derivative of the production function with respect to one specific input. Our marginal product of labor will be the partial derivative of the production function with respect to L, and the marginal product of capital will be the partial derivative of the production function with respect to K. The marginal product helps us to define the shape of the production function. There are a few different things that can happen. The best way to illustrate this is with a graph. On this graph, I'm going to put our total product on the vertical axis and quantity of inputs on our horizontal axis. This could be either K or L, it doesn't really matter. Increasing marginal returns means that marginal product is increasing as the quantity of the input increases. The shape of the production function will look something like this, where the slope is positive and getting steeper, meaning that efficiency is increasing as the amount of inputs increases. Diminishing marginal returns means that the marginal product is dropping as inputs increase. Marginal product is still positive, so total product is increasing, but it's increasing at a slowing rate. That's going to look something like this. It still has a positive slope, but it is decelerating. The final case is negative marginal returns. This means that efficiency has dropped so much that increasing outputs actually decreases the total product. That's going to look something like this. A firm would never want to be in that kind of situation. The law of diminishing marginal returns states that decreasing marginal returns must happen eventually. That's this part of our curve. It's possible to have increasing marginal returns, like over here, initially, but the law of diminishing marginal returns says eventually decreasing marginal returns are going to set in. To illustrate this, consider the example of a bakery. Suppose the bakery hires only one worker. This one worker has to do everything in the bakery. They're going to need to mix the dough, knead the dough, shape the loaves, watch the oven, clean up, do everything. If we were to start adding a little bit more labor, those workers can start to specialize and production might become more efficient. But eventually, all that equipment is going to be taken up and more workers are going to start crowding in. And even if those additional bakers are going to help increase production, they're not going to be as effective in doing so as the initial additions were. What we've just talked about are some general properties of production functions, but what we're now going to do is talk about 3 specific, well-known production functions that we're going to work with moving forward. The first production function we are going to look at is the linear production function. With the linear production function, there's a perfectly linear relationship between all inputs and output. A linear production function is going to take a specific form, which is AK plus BL. Here, A and B are just constants. They're just numbers. With a linear production function, capital and labor can be perfectly substituted for each other at a fixed ratio. From this production function, we can see that B units of capital will produce exactly the same amount of output as A units of labor. Both of them would be A times B. Alternatively, we could state this as 1 unit of labor produces exactly the same amount of output as B divided by A units of capital. The marginal product of labor of the linear production function will be the partial with respect to L. The AK term does not contain an L, so that drops out, and we're just left with B. The marginal product of capital is the partial with respect to capital. That's just going to be A. This is a very important feature of the linear production function. The marginal product of labor and capital are both constant, and they never change. These marginal products are completely unaffected by anything. The actual current amount of capital and labor have nothing to do with this. This means the law of diminishing marginal returns does not apply to the linear production function. Let's consider an example of a factory that can employ workers, that's our labor, who can each produce 2 units of output, and robots, that's our capital, which produce 3 units of output. Let's label these to make it clear, L and K. This means our production function, f of K and L, will be 3K, because each unit of capital produces 3 units of output, plus 2L, each unit of labor produces 2 units of output. This implies that 3 units of labor will produce the exact amount of output that 2 units of capital would. This also means that the MPL is going to be 2 and the MPK is going to be 3. Let's look at an example of production. Suppose we have 4 workers and 3 robots. This means L equals 4 and K equals 3. To figure out how much our factory is going to produce, we're going to plug those into our production function. So we get 3 times 3 plus 2 times 4. That's going to be 9 plus 8, which is a total of 17 units of output. The next production function we're going to look at is the Leontef production function. The Leontef production function was named after the Russian economist Vasily Leontef, who was a Nobel Prize winner in 1973. The Leontef production function is the opposite of the linear production function. With Leontef, our inputs are always used in a fixed proportion, meaning that inputs are not substitutable at all, whereas in the linear production function, they are perfectly substitutable at a certain ratio. Leontef production functions look like this. Q equals f of k and L, which is the minimum of A, K, and B, L. Again, A and B are just constants. How this production function works is we plug in K, plug in L, and whichever is lower of A, K, and BL, that's the production. This means that a ratio of B units of capital to A units of labor is always going to be the most efficient. If we go out of that ratio, we're always going to have some wasted inputs. Let's think about an example where we have a lumber company with two inputs, lumberjacks, that's our labor, and cross-cut saws, that's our capital. It takes exactly 2 lumberjacks and 1 saw to cut a log. 1 lumberjack stands on each side of the saw. If we have extra saws with no lumberjacks to use them, they do nothing. If we have extra lumberjacks with no saws, they can't do anything either. So we need to use these in a fixed proportion of 2 lumberjacks for every saw. This means our production function is going to be the minimum of K and 1/2 L. Here, A is 1, B is 1/2. What this means is that for every 1 saw and 2 lumberjacks, we can cut a log. Let's do an example of production here. Suppose we have 10 lumberjacks and 6 saws. Plugging this in, we get F of 6 and 10, which is the minimum of K, which is 6, and 1/2 L, which is 5. To use the min function, we take the lower of the two, so we're going to be able to cut 5 logs. This means that that 6th saw was completely useless here, didn't do anything. Let's think about the marginal product of labor and capital for the Leontef production function. Remember that to be efficient, the ratio of capital to labor must equal the ratio of B to A. If we are already in that ideal ratio, adding either capital or labor is not going to do anything. So for example, if we already had 10 lumberjacks and 5 saws, adding another lumberjack without adding saws does nothing. Adding more saws without adding lumberjacks also does nothing. So if we're in that ratio, the MPL and the MPK are both 0. However, if we currently have too much capital, that is K over L is bigger than B over A, adding more labor is going to give us more output. Every unit of labor we add is going to give us A additional units of output, but marginal product of capital, since we already have too much capital, it's not going to do anything. In the third case, we have too much labor, meaning that K over L is smaller than B over A. In that case, adding more labor does nothing, but adding more capital will increase production. Our third and final production function that we're going to look at here is the Cobb-Douglas production function. The Cobb-Douglas function should look pretty familiar to you from our study of utility. Cobb-Douglas production function looks very similar to the Cobb-Douglas utility function. The Cobb-Douglas production function presents, in a way, a midpoint between the Leontef and linear production functions. With Cobb-Douglas, there is some degree of substitutability between inputs, but not perfect substitutability like with the linear production function. Cobb-Douglas functions look like this. F of K and L equals K to the A, L to the B. Again, A and B, just constants. Just like with utility, Cobb-Douglas is a very popular choice to study production because it has some very nice mathematical properties that we're going to look at very soon. The Cobb-Douglas function was named after Charles Cobb and Paul Douglas, who were early 20th century American economists. Let's calculate the marginal products for Cobb-Douglas. For the marginal product of labor, we need to take the partial with respect to L. We're going to need to use the power rule here. Since we're taking the partial with respect to L, the K comes along for the ride like a constant. For the L part, the B comes down, and then we subtract 1, so we get B minus 1. We can do the same thing to calculate the marginal product of capital. Take the partial with respect to K. This time, the L to the B just comes along for the ride. Then we do the power rule for the K to the A part. A comes down, and then we subtract 1. So we get A, K to the A minus 1, L to the B. As always, I've chosen to maintain the order here. You don't necessarily have to do that. Order does not matter with multiplication. The thing to point out here with these marginal products is that they both contain K and L in them, meaning that the marginal product of labor depends on the current level of capital and the current level of labor. This again contrasts the linear production function where the marginal products did not depend on K and L. Let's look at an example. Suppose our Cobb-Douglas production function is K to the 1/2, L to the 1/2. We can do an example of production by plugging in some numbers. Suppose we have 9 units of capital and 16 units of labor. Our total production is going to be 9 to the 1/2 times 16 to the 1/2. Remember that 1/2 powers are just square roots, so we have 3 times 4, which is 12. Let's do our marginal products for our example. The marginal product of labor will be 1/2, K to the 1/2, L to the negative 1/2. Again, remember that the K to the 1/2 just came along for the ride. We took the 1/2 power from the L, brought that down, and subtracted 1. Marginal product of capital is going to look very similar. This time the 1/2 from the K comes down, and we subtract 1 to get negative 1/2. This time the L to the 1/2 just comes along for the ride because it's treated as a constant. If we wanted to figure out what exactly the marginal products are here, we can then just plug in numbers for K and L, for example, the 9 and 16 that we used earlier. That is where we will stop for now. In the next video, we're going to continue digging a little deeper into production functions.